Good afternoon. Today is the next lecture in the course Laser-Matter Interaction, and it will be dedicated to the problem of nonlinear optics. Let me summarize what we expect in linear optics. So in linear optics, if there is a linear relation between electric field of light and polarization, you do not expect that polarization would be at a different frequency than the electric field which induced this polarization. So the frequency of light cannot be altered by its passage through the medium. The properties of the medium, like chi, doesn't change on the electric field. So chi is always chi refraction coefficient. It doesn't depend on the intensity of light. Principle of superposition holds for this reason. It means that if you have interference of two waves, it will be observed exactly as interference of two waves. There will be no extra parameters in this system. And light cannot interact with light. So for instance, this example of Star Wars, you can say it's one of the examples of nonlinear optical phenomena where light interacts with light. If one of the postulates is violated, light-matter interaction, like in this particular case, must be treated as a nonlinear optical process. Where does nonlinear optical phenomenon come from? Let me first remind you that when we were talking about light-matter interaction, we found at the very first lectures, we found that the model of harmonic oscillator appears to be very powerful for this purpose. Let's try to apply this model again and see what do we have to change in this model to get nonlinearities. When we are talking about linear optics, we introduce this restoring force as something which is proportional to the displacement of electron from equilibrium. Why it was possible at that time? It was possible because we assumed that potential energy is dependent on the coordinate, had the simplest form, and since force acting on the medium is given, in this particular one-dimensional case, is given by the gradient of the potential energy, and in this particular case by the derivative of the potential energy with respect to the coordinate, we have this linear dependence, and as a result of it, we found that the response of this harmonic oscillator corresponds to the response of a linear optical system. But now we want to understand what do we have to change in this model to get nonlinearities, and in particular, what do we have to change here to be able to describe effects like second harmonic generation, so that if you shine light at the frequency omega, there is light at the frequency to omega coming out, and the phenomenon of optical rectification. So when you pump medium with a light at the frequency omega, you induce here polarization at zero frequency such that if you put here contacts, you will be able to measure voltage. Where does optical rectification, for instance, come from? My statement is that optical rectification is very similar to thermal expansion. Just with the following example, I would like to show you that thermal expansion is a phenomenon that crucially depends on anharmonicities. Well, let's consider an atom and a crystal lattice, and we try to find expectantial value for this atom. So normally in statistics, if you want to find expectation value, you have to calculate this integral, where f as a function of x is a statistical distribution, such that if you take integral from minus infinity to plus infinity, it must be equal to 1. In our case, f will not be statistical distribution. That's why the calculations of the expectation value would be slightly different. As I said, we will use Boltzmann distribution for the calculations, where U would be, as a function of x, would be the dependence of the potential energy of the atom on the coordinate. And then here we will have to calculate integral like this. And here below we will have to use normalization for the reason that Boltzmann distribution is not statistical distribution. If you put here the simplest expression for the potential energy as a function of the coordinate of the atom, you will not be able to explain thermal expansion. You will not be able to show that the expectation value of the coordinate of an atom depends on temperature. And you can see it already from this expression. So if you put here x minus ax squared divided by kt dx, and here we write also an integral this is x, this is odd function with respect to 0, so basically it changes sign at 0. This is even function with respect to 0. It is absolutely symmetric with respect to 0. You can see already from here that this integral from minus infinity to plus infinity must be 0. And it means that the expectation value is equal to 0. That means that the coordinate of the atom does not change with temperature. It's always the same. But now I add here an additional term. And adding an additional term also assuming that this term is much less, this term divided by kT, the thermal energy. K here is a Boltzmann constant. Yes, by the way, it's not, it is a Boltzmann constant. If we assume that this is less than 1, it's very small, much less than 1, then this expression can be written slightly differently. X. And we see already that we have shown this already, that there would be two integrals here and the upper side of this expression, and this part of the integral x times exponential times 1 would be equal to 0. And what we obtain here is an expression like this, from where it follows that the expectation value of the atom is a function of temperature. Basically, it means that we have been able to describe thermal expansion only by including unharmonicities. Because here I had to add an additional term to the potential energy, and the term is the next term in the expansion, and it means that if you calculate the restoring force that would correspond to this potential energy, it will contain a part which is proportional to the displacement plus a part which has a quadratic term. And if the restoring force is defined like this, oscillator, which will experience this restoring force, will not be called harmonic. So basically, I showed you here that if you want to understand thermal expansion, you have to add unharmonicities in the motion of atom, and you have to add other terms in the potential energy of atom. And basically, it is very close to the phenomenon of optical rectification. So let's look at the situation of an atom in the crystal lattice. If the temperature is very low, atoms vibrate and do not feel each other. You increase temperature, the amplitude of vibrations becomes larger and larger, and eventually, after a certain temperature, they start feeling each other, and then we have to take this term into account. So that's, if you look, for instance, at the temperature dependence of thermal expansion, up to certain temperatures, there is hardly any expansion, and the coordinates of atoms in the crystal lattice start to change only starting from certain temperature, which corresponds to the amplitude of the atomic oscillations that such that atoms start to feel each other. Very similar you can expect from electrons. If you have atoms and then there are oscillating electrons around atoms, then you come with a small electric field, oscillating electric field of low amplitude. Then oscillating electrons will only feel local environment. So they will most likely only feel the ion around which they oscillate. And it means they will only feel the very first term in this expansion. But then, when you increase the amplitude of the oscillations more and more, eventually electrons start to feel other atoms and also each other probably. And in this case, you have to take into account also this term. If you talk about non-centrosymmetric medium, it means that positive direction of x-axis would be different than negative direction of x-axis, and the potential energy may have this shape. It's exactly what I want to say by introducing this additional term. So basically, the lack of center of symmetry and appearance of this term and the potential energy, these are strongly coupled things. Now, we add this cubic term, as I just showed already. It implies that electron appears in a realizes that it is non-central symmetric environment. Let's try to see what this term would mean for the equation of motion for the of an electron. So I write this very simple law, which is called second law of Newton. We put here restoring force in the form of negative derivative of the potential energy with respect to the coordinate, and let me define this slightly different, such that this potential energy, let's define it like kx squared divided by 2 plus some coefficient x cubed divided by 3, such that restoring force will have two components, minus kx and plus term with x in square. So we put this term into this expression, and what we will get here, so it's minus x plus kx minus x squared an expression like this, assuming that electric field is 0. Just for simplicity. Then what we do, we define x as a sum of linear and nonlinear parts. So the linear part of x, the linear part of the motion of the electron, will satisfy the equation of harmonic oscillator, which we have derived before. Так, Ром, подожди. Так, тут я тоже маленько наврал. Так. Сейчас. Сколько всего слайдов здесь? Здесь немного. Мне еще всего 6. Да. Давай отсюда начинаем. Plus q e as a function of time. What we will do, we will search for solution x as a sum of linear and nonlinear parts, where for linear parts it would be just an expression for harmonic oscillator, which we have derived previously. Here I know already the coefficient k here. It would be mass times eigenfrequency in square. And this driving force. And for equation that takes nonlinear part into account, I have to write the sum of both components. course, here we shouldn't forget to put square because it's anharmonic contribution. Then we find the difference between this expression and this expression and see that the second derivative of the linear response with respect to time in this expression will be cancelled out by the very same derivative in this expression. That only the second derivative of the nonlinear part will survive. Here, this m omega 0 square x linear, and here we also have m omega 0 square x linear, they will be also cancelled out, and only term with nonlinear part will survive. Of course, driving forces are equivalent, they will be also cancelled out. And what we have left with is this. But here we also assume that linear part is much larger than non-linear part. We actually assume that here everything would be dominated by XL linear in square. And what we have at the ends is also equation of harmonic oscillator for XNL. But look what's going on here. It is equation of harmonic oscillator where linear part in square becomes the driving force. So basically, nonlinear part will, if you want to find the expression for x nonlinear, you will have to put here expression for x linear, which is xm exponent I omega t plus complex conjugated. And we know that if you take this and square, then nonlinear part will have a contribution that does not depend on time, as I have shown that already, and a contribution at the frequency 2 omega. So basically, adding anharmonicity, we have been able to show that this very first anharmonic term in the potential energy is actually responsible for the second harmonic generation and rectification. Because, as I showed at the second lecture, if you know the equation of motion for the electron, from the equation of motion of electron, you can calculate polarization induced in a medium by the electric field of light, simply taking the charge of electron, multiplying with the concentration of electrons, and multiplying with actual coordinate. So since here the coordinate will have contributions that oscillate in the frequency 2 omega and 0, it will give us polarization that will be either oscillate in the frequency 0, basically constant polarization, and the polarization at the frequency 2 omega. So basically, these are phenomena of optical rectification and second harmonic generation. Well, this was just the very first anharmonic term added to the model of an oscillating electron, and if you add terms of higher order, like if you have potential energy that is described by, of course, this dominating term, which is eventually responsible for harmonic response of the oscillator, plus this anharmonic term, first anharmonic term, which is responsible for second harmonic generation and optical rectification. You can also think about the next term, And in accordance with analogy, which we had here, if you had this term, you can get effects in the optical response of the second order with respect to the electric field of light, like optical rectification and second harmonic generation. If you add unharmonicity of the next order, you can have two other effects. It's basically adding here additional electric field, and it would give me third harmonic generation. And here, adding additional electric field would give me something weird, because polarization would be still oscillating at the frequency omega. What does it mean? It is nonlinear optical effect on one hand, but the polarization is still oscillating at the frequency omega. How should I understand it? Let's now look at this weird effect, nonlinear polarization that oscillates at the frequency omega. How would this polarization affect optical properties? Let's consider total polarization as a sum of linear and nonlinear part. So both these polarizations are at the frequency omega. Nonlinear part will be defined by this expression. Just for simplicity, let me define it for isotropic medium. As you can see, if you now use operation of space inversion, this will change sign, this will change sign, this will change sign. And this polarization must change sign as well, and it means that there are no restrictions on this tensor, and it means that we can observe effect which is described by this expression in any medium by symmetry. So we find this we write this in a simple form, and obviously this linear polarization, it would be nonlinear. This would be a linear function of the electric field. Okay. Now we write this total polarization. And you write this expression slightly differently. And you can see that this part can be treated as an effective optical susceptibility, which will consist, the biggest part of it will consist of the linear susceptibility, and next to this there would be a part originating from nonlinear optical effect, which is proportional to the square of electric field. And then you know that this is actually intensity of light. So we can rewrite this expression simply like P at the frequency omega, polarization induced in the medium by light, is proportional to the electric field of light, but this chi becomes a function of intensity, because it's chi effective already, because of this term. Let's now try to figure out what this exactly means. Linear plus nonlinear E omega E complex conjugate omega. And we know that refraction coefficient is a square root of epsilon, and epsilon is chi plus 1. Then, obviously, if we have an addition, a correction to the optical susceptibility that depends on intensity, it means that also refraction coefficient will have some correction to this to itself, and this correction would be due to this nonlinear contribution to the optical susceptibility. So we write this n, well, effective. Okay. So we write this n effective like n plus delta n equal to chi effective plus 1 n plus delta n in square will be chi effective plus 1. N in square plus 2n delta n plus n delta n in square plus 1. Then we also assume that delta n is much less, and this gives me that n plus 2n delta n is equal to effective plus 1. Then effective, don't forget, it is linear part plus chi nonlinear E omega star, where n is just n square, is just linear plus 1. From where you can see that 2n delta n must be approximately equal to x nl E omega star, and this actually gives me that if you add this nonlinear part to the response of the polarization with respect to response of the polarization to optical excitation to the electric field of light, we arrive to a very simple expression for a correction to the refraction coefficient, which is proportional to the intensity of light, which is proportional to the electric field times electric field star. So basically it means that due to this nonlinear optical contribution, we have a refraction coefficient that depends on intensity, that depends on light intensity. And this phenomenon is called photorefraction. How do we see it experimentally? Well, experimentally, you will see it in particular in the effect of self-focusing. If you take a laser beam, again, taking laser beam is important because we are talking about nonlinear optics. And nonlinear optics means taking into account higher terms in Taylor series, with higher terms in the Taylor series for polarization with respect to the electric field of light. If you want to take terms of higher order, you have to take more and more terms into account in this Taylor series, and it means the electric field should be larger and larger. As a matter of fact, in order to observe nonlinear optical phenomenon, you need a laser, because only laser provides electric fields strong enough to excite nonlinear optics without destroying, to excite nonlinear optical phenomena without destroying the sample. Okay, we take a laser, and lasers produce so-called Gaussian beams. So if you look at the intensity of laser beam, so this is intensity, this is coordinate, it will be described by Gaussian shape. If you take into account this nonlinear contribution to the refraction coefficient experienced by light here would be different than the refraction coefficient experienced by light here. So, for instance, we assume that this chi nonlinear is positive. So it means that the refraction coefficient here in the center of the beam would be larger. So it means that light, while propagating, so now this is the coordinate, this is a light wave front. So that then light, while propagating, it was just a plane front, and then here in the center it will experience larger refraction coefficient, and it would be delayed with respect to the light at the edges of the beam. Then we apply Huygens principle, so it means that every point on this wave front would be source of new wave. So we draw new wave around each of these points, and you will find that all these waves and all these points will actually interfere constructively somewhere on the axis. So it means that we will have focusing, self-focusing. So the focusing induced by light itself. So light will focus itself. So if you shine with a very strong, very intense laser beam on a thick piece of glass, for instance, it will be already sufficient to observe effect of self-focusing. If chi is positive. If chi is negative, then we will have the opposite effect, defocusing. And these are two phenomena, these two manifestations of a phenomenon which is called photorefraction. Finally, I would like to come with a few more examples. And the next two examples, they are just in the border between linear and nonlinear optics. Just imagine that I'm talking about linear optical phenomenon. So the polarization induced in the medium by light is a linear function of the electric field of light, and here I have optical susceptibility. But this optical susceptibility also depends on vibrations in the crystal. For instance, lattice vibrates, right? Lattice has eigenfrequencies, so-called phonon frequencies, frequencies of phonons. So imagine that lattice oscillates with a certain frequency, with a certain phonon frequency, omega 0. So now, if you put here chi oscillating at omega 0, and if you simply multiply these two oscillating functions, you will see that polarization, which will be induced by these two oscillating functions, would be at the frequency omega minus omega 0, and the frequency omega plus omega 0. So basically it means that if you shine light on a surface, and if you measure very carefully the spectrum of light, here, of course, there would be light. If this was at the frequency omega, there would be light reflected at the frequency omega. But if you measure frequency very carefully, you will be able to detect a part of light at the frequency omega minus omega 0 and the frequency omega plus omega 0. And this effect would be called scattering. Historically, people distinguish Brillouin scattering and Raman scattering. If Raman scattering is more related to scattering of light by optical phonons, Brillouin scattering is related to scattering of light on acoustic phonons. Another effect I would like to explain you allows to induce in a medium magnetic field. So light can act as a magnetic field. How is it possible? Well, again, if you start with the first law of thermodynamics, internal energy, work performed on the system, and Q is the heat transferred to the system. We assume that we do not transfer any heat, and work performed on the system would be E times dP, and after integration you will see that work would be epsilon 0 chi j E I omega E j star plus some constant, integration constant. And also thermodynamically, you can say that effective magnetic field experienced by magnetization in a medium can be calculated as a derivative of the internal energy with respect to this magnetization. So if you take derivative of this expression with respect to the magnetization, you will see that the only parameter that depends on the magnetization can depend on magnetization is this. Chi, optical susceptibility. And we did see that chi does depend on the magnetization indeed, and in particular, if we take into account linear term in this dependence, we will be able to show so-called Faraday effect, magneto-optical Faraday effect. The fact that when linear polarized light propagates through a medium, polarization of this linear polarized light rotates a certain angle, and the angle of rotation would be proportional to the magnetization. So this Faraday effect, magneto-optical Faraday effect, originates from linear dependence of chi. So if you take this linear dependence into account, you will be able to calculate that this derivative is not equal to 0, and it means that light can create in a medium effective magnetic field that would act on the magnetization. It is not real electric field, it's not real magnetic field, it is not magnetic field that one would generate with the help of electromagnet, but it is a sort of force that will break the degeneracy between the states with magnetization up and magnetization down. Or strictly speaking, it is derivative of internal energy with respect to the magnetization. This is another example of nonlinear effect, and I think I have given already enough examples in order to prove that in nonlinear optics, light can change properties of media, light can interact with light, like in the case of photorefraction, for instance. In the case of second harmonic generation, light can change its frequency. And in terms of model of classical oscillating electrons, the origin of nonlinear light-matter interaction is just unharmonicity of the oscillators. Thank you very much.